Hello, and welcome to my lecture on Chapter 1 of Conceptual Physical Science, 6th edition by Hewitt. Since this is a textbook that covers all of physical science, these lectures will cover the topics of physics, chemistry, geology, and astronomy. So, a lot of things to talk about. But we're going to start with the very basics of understanding the physical world. And that's what this chapter is all about. If we look at the title, we see it's patterns and equilibrium. Equilibrium being another word for balance, really. So that's a great place to start. Look at the physical world around us and acknowledge the patterns and balance we see in that physical world. Okay? But what does that mean? Because it's a pretty vague idea. Well, let's take a look. We're going to go back in history to the very beginnings of questions in recorded history that were about the physical sciences, questions about the physical sciences proposed by people like Aristotle. We'll then move into a point in history known as the Renaissance, where we had our more modern views of the physical sciences, our more modern views of science in general, starting with characters like Galileo, then moving into some very important ideas, mass, force, that idea of equilibrium, balance as a rule, talking about particular very common forces we see in our everyday lives, like the support force. Talk about more cases of things being in balance. In this case, you can be balanced in emotion. You don't have to be perfectly still. In fact, no one is ever perfectly still. Think about that. We'll get more into specific forces. And then we're going to finish off with what's known as kinematics, which is the word that scientists use for this field of study, which is just the study of things moving. That's speed and velocity, and then acceleration, speeding up and slowing down. Okay? And this also involves turning when we talk about speed and velocity and acceleration. Okay? So that's what this introductory chapter is going to be all about. The patterns part being this idea of forces. Forces are acknowledging the patterns of the natural world, as are the ideas of acknowledging the relationship between velocity and acceleration. And then, real important idea that shows up a few times, this idea of equilibrium. Okay? All right, let's get into it. So, going back into ancient history, over 2,000 years ago, we had Aristotle, who classified motion into two kinds. Okay? Now, is this the same classification we use today? Absolutely not. This is not how we classify motion anymore. But this was the beginnings of asking those big questions. Is the natural world just totally chaotic and unfathomable? Or is there a guided way to look at the natural world? And Aristotle said, yes, there's a guided way, and there is natural motion and violent motion. Okay? And that was it. Things would fall into those different categories. And there was a whole structure of other ideas that was based around this, including the elements, the ideas of fire and earth and air and water. Okay? Now, those ideas held on for over 1,500 years. But by the time of the 1400s, we had people like Galileo, we had people like Newton, we had people like Kepler that were thinking outside the box. We're thinking revolutionary new ideas, new ways of looking at the physical world. Okay? And they wanted to find new rules, rules that were observable, that were testable, that other people could repeat. Because Aristotle's rules were purely from the imagined mind. They were just philosophical ideas. They were not testable. Well, one of these testable ideas was the concept of inertia. The Italian scientist Galileo demolished Aristotle's assertions in the early 1500s. In the absence of a force, talk about that more, objects once set in motion tend to continue moving indefinitely, which is to say forever. Okay? That's what inertia is. It's a property of mass. If things are in motion, they'll continue in motion unless something stops them, like air resistance or friction in our everyday lives, right? Drag as a boat floating in the water, okay? But if you were in the vacuum of space, things just continue to move forever. And the final position, well, it could be infinitely far away if nothing ever stops this object with inertia, a property of matter. Okay? There's a legend of the Leaning Tower of Pisa that involves Galileo, where Galileo showed that dropped objects fall down that tower to the ground at the same time when air resistance is negligible. Okay? So we could have, say, a wooden sphere and a very dense metal sphere. But since they're both the same size and shape, they're both going to experience about the same air resistance. So they're both going to fall exactly the same way, even though the wood might be 1/10 as heavy as the metal. So the weight of the object doesn't make it fall any faster. Okay? Now, that's a really important idea. How does that tie in with inertia? Well, it wasn't immediately evident, but it definitely showed that the rate at which things sped up when they're in free fall was independent of their mass. So, continuing with the discovery related to the concept of inertia, we can say that in the absence of friction, no force is necessary to keep a horizontal moving object moving. This is an important statement because it restates what I said a moment ago about an object just continuing to move forever unless something stops it. Well, this is just pointing out that you can move forever, continuing to coast along, neither speeding up nor slowing down nor turning. You can continue to coast along forever because there's no force necessary. Okay? Okay. Let's consider an important experiment to understand this idea. Balls rolling down inclined planes and then up the other side of the inclined plane tend to roll back up to their original height. Okay? So we see that there was some force that pulled them down. Again, more on forces in a moment. And then when they go back up, there's still a force pulling them down. So they're only able to exchange equal amounts of going down for going up. And it doesn't matter if it's a longer path going up because the planes have very little friction. So the only force is the force in the direction I drew, the arrow direction. The conclusion then is that the tendency of a moving object, body, physicists often call objects bodies, okay, to keep moving is natural. Every material object resists change in its state of motion. This property is that property of matter. That's inertia. Okay? Now, I don't want inertia to be a purely conceptual idea because I do see people sometimes get confused with inertia because it seems too high-minded and too abstract. So one thing to ground inertia, as we'll do with other physical concepts, since it is a property of mass, it has units. Okay? It has units of kilograms, which are, of course, the same units as mass. Because mass and inertia are the same thing in some contexts. Basically, it just depends if the object is rotating or not, and exactly how you define mass. But as far as this idea of kilograms as you'd weigh on a scale, those kilograms are the units of inertia. It's a physical quantity with units, okay? And it's just mass. And it's the body's tendency to just keep moving unless something stops it. Or for an object to stay at rest unless something perturbs it or disturbs it from rest. So, mass is inertia, okay? Just two ways of saying the same thing. The amount of inertia possessed by an object depends on the amount of matter, okay? As we'll talk about later, the number of atoms that compose that object, the amount of material that composes it. It's mass. Greater mass, greater inertia. Smaller mass, smaller inertia. All right? No size here, no density, just mass, right? Shape doesn't matter, it's just mass. Okay? So what is mass? It's a quantity of matter, okay? Way to quantify matter. It's the measure of inertia. Now, a great way to think about inertia is the sluggishness that an object exhibits, okay? It's a great way. It's a great way to remember it. Inertia, mass, is the sluggishness of matter. Okay? That means that things that have more mass, thus more inertia, are harder to get started moving. And they also take more to stop them. Like this person pushing on an elephant, it's hard to get the elephant to start moving. You have to push a lot in order to get the elephant to move at first very slow speed. See? Because an elephant has a lot of inertia. It resists change. Okay? Now, what about weight? Because a moment ago I said that kilograms are like that unit you might be used to when you change the unit display on your scale. If you're used to measuring the weight of things in pounds, but if you push a little button on your scale and it changes over kilograms, right? Kilograms are a weight, but they're also a mass. Well, what's the difference, right? What is the difference between weight versus mass? Well, it's an important difference, okay? Because mass is inherent. It's the actual atoms. It's as if we're counting the number of atoms that are in an object. That's its mass. Weight is gravitational pull, okay? That means that weight, as we know it, is completely arbitrary to Earth. If we go to a different planet, we'd have a different weight, but we'd have the same mass, okay? This is an ideal that we'll return to, okay? Now, weight is proportional to mass. So, for example, on Earth, if everyone is on the same planet, everyone's on Earth, if I have greater mass, I also have greater weight. And the ratio of how much more mass I have to how much more weight I have to someone else is the same, because we all experience the same pull of gravity on Earth, okay? All right. Twice the mass, twice the weight. Half the mass, half the weight, okay? So, mass versus volume. How do we relate that? Because I mentioned size, that inertia is independent of size, but what about when we do care about size? Well, mass involves how much matter an object contains. That's it, okay? Volume involves how much space an object occupies. So mass and volume are complements of each other. One doesn't depend on the other. They're totally independent, right? So obviously you can have an object that has very high mass and very small volume, or you can have an object that has very high mass and also very large volume, okay? So let's do our first concept question and our first check. There'll be these checks throughout the lectures. The concept of inertia mostly involves, if you don't know this one, you need to go back and review, okay? Mass. Made a big deal that they're synonyms for each other, all right? Okay, so the unit of mass, mentioned before, here's the full name, kilogram. Before I wrote it as in parentheses as kg, that's the way you're typically going to see it. It is the standard unit, okay? This is the metric system. This is the standard unit of measurement for mass. On Earth's surface, 1 kilogram material weighs 10 newtons. Yet that's specific to Earth because of our value of gravitational pull, which we call gravitational acceleration. Away from Earth, on the moon, 1 kilogram of material weighs less than 10 newtons. Why? Because the moon is smaller and it thus has less gravitational pull. Everything's lighter on the moon. Things have the same mass on the moon, but less weight. Okay? So, more concept questions. Thinking about inertia here. When the string is pulled down slowly, the top string breaks. Which best illustrates what? What are we asking here? So first, really imagine that. Imagine you're pulling that top string. You're kind of just gradually pulling a little bit more, pulling more on that weight, right? It would be equivalently, gradually pulling more would really the same idea as like continuing to take like little hooked weights and adding them on one at a time. Just adding a little bit of weight to the end, okay? So when that happens and you break this upper string, what idea does that best illustrate? Weight, mass, volume, or density? Take a moment and answer it. Weight. Because as I hinted at, by pulling slowly, you're effectively adding more weight to the hanging ball. But you know what's interesting? It's not always the top string that breaks. Okay? So if the string is pulled quickly, so the hand pulls down really fast, okay, pulls down super fast, the bottom string will break in that case. What idea does that illustrate? What concept does that illustrate? Right? You're trying to pull really fast, essentially trying to accelerate this hanging weight very quickly downwards. And he doesn't want to. He doesn't want to move very quickly downwards because it's sluggish. So what idea does that illustrate? The mass. It illustrates the inertia. Okay? So it's this two cases of the upper string and lower string breaking really illustrates, I feel highlights the idea of how physics sometimes seems subtle or contradictory, but it's not. It's just a matter of these are different circumstances. Pulling fast versus pulling slow have very different criteria. These are very physically distinct situations. Okay, so a little bit more about mass, okay, and its relationship to volume. Okay, so we're combining mass with volume now to give us density. And it's a measure of compactness, right? Something's more dense, it's more compact. Something's less dense, it's less compact. Density is the measure of how much mass occupies a given space. So that means as an equation, it's mass over volume. Symbolically, density, usually represented by the Greek letter rho, would then be equal to m over uppercase V for volume. M for mass, by the way. Okay? Units here, kilograms for the mass. Volume, what are the units there? Well, it's a space, so three-dimensional, and you take the standard unit of distance, so it's cubic meters. Cubic meters. Okay? It can be also measured in grams per cubic centimeter, all right, or kilograms per cubic meter. These are not numerically equivalent. I'll leave that as an exercise, but they are still both metric units, but with different prefixes of size, because a centimeter is 1/100th of a meter, and of course a kilogram is 1,000 grams. Okay? Okay. So the density of 1 kilogram of iron is what? Less on the moon, the same on the moon, greater on the moon, or could they all be right? That doesn't seem likely. So which is it? Make sure you can answer it. The same. Why is that? Because volume and mass are independent of gravity. It was only weight that depended on gravity, and it's only gravitational pull that changes between Earth and the moon. Okay? And again, we'll get into the reasons for that in a later chapter, why there's less gravity on the moon, but suffice to say it's because the moon is smaller. Okay? Okay, so we've established really our first unit, our first physical quantity, the kilogram. Okay, now we did a few other things in there too. We talked about weight, we talked about density and volume. Okay, but really we've kind of established one of the big players, the kilogram, mass. Okay, but now we're going to talk about a new unit, a new physical quantity, and that is force. Okay, force is measured in newtons. I'll be saying this again in a later slide, but that is the unit, just like kilograms are the unit of mass. Okay, so what is force? It's simply a push or a pull. Okay, so you can exert forces on the world around you, right? Using your limbs or parts of your body, pushing things, you pull on them. Okay, gravity pushes and pulls on things. Okay, in fact, actually, gravity only pulls. Okay, there are other forces as well. There's these electromagnetic forces, right? Don't come up too much in our everyday lives, but they push and pull. Okay. And the net force is the total force. Okay? Net is a word that's used quite a bit in the physical sciences, and it just means total. You're summing something up. Okay? All right, so if you got four separate forces acting on an object, right? Maybe there's a string tied to it, someone's pulling on it, there's some friction, right? The ground is pushing up from below, okay? Gravity, right? So you got a bunch of different forces acting on one object. If you sum them all up, then you get the net force, okay? It's a combination of all forces that act on an object. All right, and it changes an object's motion. The net force has a direct effect on motion. But of course it does, right? That's what brakes do. You slam on your brakes, they slow your car down. That's because once you slam on your brakes, your net force on the car is pointing backwards relative to your forward motion, and it slows you down. Okay? So let's look at some cases of applied forces. Imagine there are two sets of forces represented by these pink arrows. They each have values of 5n, but you can guess what the n is. That's the unit of the force. That's the Newton. Okay? Right? So they're both 5 newtons. A 5 Newton force is not a particularly strong force, by the way, if you're thinking about the strength of forces. If I was to pull on something with as much force as I can, like pulling on a big heavy box, I'd be pulling with about 400 newtons of force. Okay? If I'm maybe just like don't have good footing, maybe 200, right? But those are your larger pulling forces. So 5 here is on the small side, not tiny, but small side. Okay. Well, if both those forces are pointing in the same direction, in this case to the right, then we'd say the net force, the total summed force, is just 10 newtons. Makes sense, right? Now, what if you had two forces pulling in opposite directions? Well, in that case, you'd imagine, well, they cancel out, right? Well, exactly. The net force is zero. And that, again, would affect motion, wouldn't it? Because in this case, the object is going to start accelerating in this direction, A for acceleration. But in the direction where you got the forces, one to the left and one to the right, and they're equal in value, and the object thus is staying still, right? Well, then the acceleration is zero. We'll talk about that again, okay? But you could have two forces on either side, but have them be unequal, have one larger, the force to the right be larger. Well, then there is still going to be a net force, right? How do I get that? Well, I take 10, okay, and then I'd subtract 5 to get 5, right? Just as we did 5 plus 5 in the case where they're both pointing in the same direction. What's a good takeaway from this? Direction matters, okay? Direction definitely matters. Forces are what are known as vectors, and direction matters, okay? Force is a vector. All right. A cart is pushed to the right with a force of 15 newtons, while being pulled to the left with a force of 20 newtons. The net force on the cart is what? Make sure you can answer this. 5 newtons to the left, okay? Now, what is the equilibrium rule? Okay, so we got forces. We'll come back to forces, some particular cases of them, but we want to move on to one of the other big parts of this lecture, the idea of balance equilibrium. Okay, so what is the equilibrium rule? Well, it says that the sum of forces acting on a non-accelerating object or system of objects equals 0. Okay, so what does that mean? It means that if there's no acceleration, non-accelerating, then net force is 0. So it's saying if one of them is true, then the other also must be true. Okay, so in mathematical notation, we say the sum of forces, which we can also write as F with a little net to remind us that it's net force. So I add a subscript of net. If that equals 0, then acceleration must also equal 0. Okay? And you could read this sentence either way. I could rewrite it and say, if the acceleration equals 0, then F net equals 0. See, it goes both ways. One necessitates the other. Okay? That's the equilibrium rule related to forces. Okay? So an object that moves at constant velocity, okay, constant velocity, is in equilibrium. That's called dynamic equilibrium. Because you can have things that are at rest, and that's maybe the first thing that comes to mind when you think equilibrium, balanced. Okay, you build a building, you don't want the building to tip over, it's in equilibrium, it's balanced out. The forces are balanced, okay? Right? The Leaning Tower of Pisa is in fact balanced, it's not tipping, right? But it happened to reach an equilibrium where it's a little to the side, okay? But those would be balanced objects at rest. But you can have things that are coasting along. Think that first, inertia rule from Galileo, things that are coasting along at constant velocity, and they are in equilibrium. Why? Because they're not accelerating. They're not slowing down, speeding up, nor turning. And that means that they're in equilibrium, okay? That means the forces are canceling out to 0. F net equals 0. If this thing is moving at constant velocity, so V for velocity is a constant, then I know right away that F net equals 0. In other words, the pushing force from the woman here, F push, that's just F for a force, push because I wanted to name the force, would be exactly equal to the force of friction, F friction. Those two forces, one points to the right, the pushing force, the other one points to the left, the friction force, they're exactly equal and they cancel out. But that doesn't mean the table remains at rest. It means just coasts along at constant speed. Now, in order to get the table from rest to that constant speed, there would have had to be at least a little moment where the pushing force was greater, okay? So you had to push a little bit more at first, but then you could continue to push with a little bit less to keep it moving, okay? So the bowling ball is in equilibrium when what? When it's at rest? When it moves steadily in a straight line path? Both or neither of those equilibrium? All right, well, hopefully you recognize it's both, because we've talked about objects being at rest and dynamic equilibrium, and that's the cases. Straight line path, constant speed, that's dynamic equilibrium, okay? At rest, we would call this stable equilibrium or at rest equilibrium. Okay? All right. Back to specifics about forces. Because, we got the force of gravity, something I've hinted at a bit. Haven't gone into too much, especially because it has its own chapter later on. But that's certainly a force, one we can hopefully conceptualize as an everyday force. But another really important everyday force is the support force, which, by the way, is also called the normal force. All right, and I'll probably call it that. I'm more used to calling it the normal force, although the support force is a less idiosyncratic name, less like jargon. I think the support force is a good name, just not the one I'm used to. Okay, so what is the support force? Well, it's the force that supports an object on the surface against gravity. So if I am an object, like a book, resting on a table, the table pushes back. That's the support force right here. The table pushes back. It's the supporting force. But it's supporting against what? Well, of course, gravity. Because gravity always wants to pull on objects. Gravity doesn't care that there's a table in the way. Gravity's still going to pull on the object, right? Gravity pulls on everything on the surface of Earth. But if you're not just free falling, then something's supporting you, preventing you from falling. Well, that supporting force is the support force, okay? And if net force equals 0, which is shown in both these pictures, isn't it? In both the case of the spring and the table, in both cases, doesn't it look like the net force is 0 just based on the length of the arrows, right? Equal length, top and bottom, okay? Well, that means that these objects are in equilibrium. They're at rest and they're staying at rest, okay? Now, in the case of the support force on the spring, sometimes this is also called a spring force, but it's the same exact idea, okay? It's just that when we think about a table, we don't think about a table as being springy. It does have a little bit of spring, right? Probably on a tiny scale. Every object can be compressed a little bit with enough force at least, okay? But springs are a dramatic example. You put something on a spring, it's still supporting it, but the spring compresses, okay? It has its own properties. So when you stand on 2 bathroom scales with 1 foot on each scale and weight evenly distributed, okay, so you kind of balanced out, each scale will read what? What do you think? Think about equilibrium. Think about F net. Think about the definition of the support force, because that's what the scales are reading. Okay, the scales are reading the support force, yes. Okay. Think about the arrows, right? We've got 1 weight vector, which we call the gravitational force, and then we've got 2 support vectors, which is just the name for the arrows, okay? So that means that each scale must be, what must it be? Half, okay? It's divided between the 2, because you sum them up to 0. In fact, you'd have to sum up all 3 of those arrows to 0, right? Just to have your F net equal 0. Okay, another everyday important force to understand, friction. Okay, what is friction? It is the resistive force that opposes the motion or attempted motion of an object through a fluid or past another object which it is in contact with. Okay, so in a fluid, that case is often called drag or air resistance. There's another names for those. And we'll touch on that very briefly in our chapter on fluids. All right, that's a word drag, by the way. But we could also call that fluid friction. That's totally valid, right? There's some different properties. Friction is caused by a whole complicated number of factors at the microscopic scale, but it always plays by the same rules. It's always a resistive force, and whenever you're in anywhere other than a vacuum, there's always going to be some friction. Molecules rubbing against other molecules, molecules bumping into other molecules. Okay, and it always opposes motion because it is all the collisions and breaking of small things on the microscopic scale that causes friction. Okay, if there's no motion, then there's going to be no friction. Okay, all right. So friction between 2 surfaces is the most relevant to a introductory chapter that's not talking about fluids, especially since we're going to talk about fluids later. So that's terrestrial friction. Okay, and the amount depends on the kind of materials and how much they're pressed together. So how much force there is between the 2 materials, okay? And it's caused by all these complicated factors like surface bumps, stickiness, like capillary forces, electrostatic forces between the materials, okay? Some at the atomic scale, some at the molecular scale, right? That's what's going on. That's what causes friction. And so, some things are really smooth, like Teflon. You rub Teflon against, Teflon, they're so smooth against each other. Obviously, you could have, rough wood against another piece of rough wood, and that would be much greater friction, thus a greater friction force. Okay, one rough surface against the other. And for example, if I was to pull on this green block, let's assume these are some sort of rough surfaces, things that you'd imagine being resisting being pulled to the side, and I have a pulling force, then we would just draw the friction force, as going the opposite way, right? Just resisting that change. And if they're exactly equal, like I drew them, like the two length force vectors are the same length but in opposite directions, then what's going to happen to the block? It's going to stay at rest because we have an equilibrium situation here. Okay? All right. So the force of friction can occur with sliding objects, in water, in air. Well, if you're paying attention, all the above. Okay? That's all kinds of friction in the broad sense. Okay? So here's another question. When Nellie pushes a crate across a factory floor at constant speed, the force of friction between the crate and the floor is, well, is it less than Nellie's push? Is it equal to Nellie's push? Is it equal and opposite to Nellie's push? Or is it more than Nellie's push? Okay, so she's moving it at constant speed, right? It's equal and opposite. Because just say it's equal, since force has both a length, the length of the force arrow, the force vector, and a direction. Equal would not be enough, because equal would imply that it's in the same direction. So equal and opposite is important because it clarifies the direction. It's the better answer in this multiple choice here, isn't it? Okay? Okay. And by the way, if the friction force, the force of friction, was less than Nellie's push, then what would happen? There would be an acceleration. And I'll let you think about what would happen if it was greater than, okay? But there would be an acceleration in that direction. It'd pick up speed. We'll talk more about acceleration in just a moment, okay? Okay, so when Nellie pushes a crate across a factory floor at an increasing speed, the amount of friction between the crate and the floor is what? What must it be? That's what I was talking about. Because increasing speed is the same as saying acceleration that is greater than 0. Positive acceleration. Again, assuming that the positive direction is to the right. But isn't that how you read a number line? Isn't that a normal assumption? Well, hopefully, we can all be on the same page about that. Okay? So the increasing speed indicates a net force greater than 0. Her push is greater than the friction force. The crate is not in equilibrium. Okay? Definitely not. Not even dynamic equilibrium. This is an accelerating crate. It's picking up speed. Okay? All right. So we're going to finish off this lecture now by talking about some things that have been implied and hinted at quite a bit. That's motion, right? Because it really speed and velocity. This is getting to actually defining motion. All right. Well, good, because we've got that if you don't have a net force that is equal to 0, then you're going to get motion, right? So if net force is not equal to 0, okay, the equilibrium rule, but the other way, the case where things are not in equilibrium, then you're going to be like Nellie here. You're going to have increasing speed. Okay, increasing speed means you need to worry about things like speed and velocity because they're going to be changing, which is to say there's going to be an acceleration. Okay, that means we need to define these quantities. We need to define what are speed, velocity, what's the difference between speed and velocity, and how do they relate to acceleration. Okay, so speed, getting to it, is described as the distance covered per amount of time. Okay, it's distance per time. Distance per time. Okay, that's what speed is, right? As an equation, you can write it in words like this, or you could say speed, represented by S, is going to be d for distance, over t for time. Good. Okay, there's average speed, which is the total distance traveled divided by the travel time. So that means you would take the total distance over an hour, for example, and then divide by that hour, and then you get your average speed. Okay? Now that's different than instantaneous speed. See, because instantaneous speed is like what a speedometer has. It's not averaging, at least it averages some very small amount of time, because you can never have, it be truly instantaneous. You'd have to be measuring every nanosecond. Even that's not instantaneous, right? In reality, probably a speedometer is going to measure based on the rotation speed of the wheels a few times per second and then give you a readout that seems pretty darn instantaneous to the human brain, okay? All right, but anyway, you get the idea. That would be instantaneous speed, how fast you're going at that moment, okay, instead of average. So the average speed, to make sure you do have the idea, let's do a calculation. The average speed in driving 30 kilometers in 1 hour is the same average speed as driving what? 30 kilometers in half an hour, 30 kilometers in 2 hours, 60 kilometers in half an hour, or 60 kilometers in 2 hours. Think about the equation. Average speed was total distance over time. So if I double the distance, like in the case of the 60, then in order to get the same average speed, I must also double the time. Okay? So 30 in 1 hour is the same as 60 in 2. Okay, good. Now, interesting thing about motion, just a quick aside before we talk about acceleration, it's relative, because if I say I'm at rest right now, you say, I'm sitting in my chair, I'm at rest. That's a form of equilibrium. It's the other kind. It's not the dynamic kind, it's just the at rest equilibrium, right? But then, are you really at rest? Well, yeah, sure, relative to your room, you're at rest, but not relative to the sun, okay? Everything is always in motion, excuse me. At this moment, your speed relative to the sun is about 100,000 kilometers per hour. You're going incredibly fast relative to the sun, all right? The sun relative to the center galaxy is going 500,000 kilometers per hour. Incredible, all right? So when we say a space shuttle travels at 30,000 kilometers per hour, right? That's relative to Earth. That's actually not relative to the sun, all right? So some really interesting numbers there too, because that actually has some big consequences. Because if we're going that fast relative to the sun, that means that in order to actually shoot something into the sun, we'd have to bring that thing to rest, which means we'd have to shoot something in the opposite direction of Earth in order to have it come to rest and then fall straight towards the sun. But that means we have to shoot it at 100,000 kilometers per hour. So it's actually not easy to shoot something into the sun, even though you think, yeah, just aim at the sun. It doesn't work that way. If you just aimed at the sun, you'd actually just give it an orbit around the sun because of our motion, the planet's motion. Pretty cool stuff, okay? So a hungry bee sees a flower, right, from planets to bees here, in a 5 meter per second breeze. Notice this unit, by the way. This is our most common unit of velocity, meter per second. Meter per second. Okay, so 5 meter per second breeze. How fast and what direction should the bee fly in order to hover above the flower? Right, so the flower is over here, right? Our bee is right here, okay? The breeze is moving in this direction, okay? And that it's blowing in that direction at 5 meters per second. How fast does the bee have to fly relative to the ground? Well, relative to the breeze, really. Relative to the breeze in order to stay fixed relative to the ground, right? Because the bee doesn't get to choose to fly relative to the ground. It's in the air, it's moving through the air. It has to move relative to its surroundings. It has to push off the air molecules. So it's moving 5 meters per second relative to the breeze, which allows it to remain at rest relative to the ground. And I kind of answered that one for you. But if you'll forgive me, the idea here is important. The bee is moving 5 meters per second relative to the breeze, thus staying at 0 meters per second relative to the ground. Okay. It's a typical idea for relative velocity, thinking about moving in the air or the water and then staying maybe fixed in place relative to the shore or the ground. Because if I was in a river and the river was flowing towards the sea at 5 meters per second, and I wanted to swim away from the coast, so away from the sea at 5 meters per second, then I would be at rest relative to the ground. You'd see me paddling in the river and the river rushing past me, but I wouldn't move anywhere if you're just sitting on the shore. Same idea of the bee here, okay? All right, so finally, acceleration, right? So we've talked about quite a bit, because anytime you have a net force not equal to acceleration, not equal to 0, you get an acceleration, right? Right, so F net not equal to 0, I know I said it before, is such an important relationship though. Then acceleration is non-zero, okay? You get acceleration anytime there's an imbalance of forces. Okay? So Galileo first formulated the concept of acceleration in his experiments with inclined planes. Okay? And he found the idea that when the plane is sloped downwards, speed increases. Common sense, isn't it? When it's sloped upward, the speed decreases. And when there's no slope, then the speed only changes because of friction. And if there's very little friction, then it doesn't appreciably change. You can't measure the change, just coasts along. Okay? Acceleration was that quantity of the change. It's the rate at which velocity changes with time. All right, so the change in velocity may be in magnitude, in direction, or both. You could be turning and slowing down. You could be turning at constant speed, all right? Or you could be going straight and speeding up or slowing down. Those are all forms of acceleration, okay? Speeding up, slowing down, turning are all accelerations, okay? It's a change of velocity over time interval. As an equation, symbolically, it's a for acceleration equals the change in velocity, delta v, see that? Okay, over t. And this delta symbol here, okay, delta, it's a lowercase Greek, or actually it's the uppercase Greek letter for delta, all right? And that symbol just means change, and that means we could rewrite acceleration as v final minus v initial, so over some period of time, over that period of time, right? So if your acceleration changed over 1 second, you'd have your starting velocity, your finishing velocity, and then that 1 second is what you'd be dividing by, okay? So an automobile cannot maintain a constant speed when accelerating, rounding a curve, both, none. Well, I've said acceleration involves turning, so aren't these both just acceleration? Yeah, right? Rounding a curve is code, physical science speak, for acceleration, because you can't turn without accelerating, because that's a change in velocity, because velocity has both magnitude and direction. Okay, acceleration and velocity are actually much the same as each other, rates but for different quantities. The same with when direction is not a factor, they equal to each other. The same for free fall situations. Well, the only answer that makes sense here is rates. Okay, they're both rates. Velocity is a rate of distance change over time. Acceleration is a rate of velocity change over time. They're both rates, right? They're a rate of change. It's a big deal in science to have a rate of change. In fact, quantifying rates of change actually leads to the mathematics of calculus. Okay, we won't do that in this class, but that's one of the big ideas. Okay. Now, the most prevalent form of acceleration is free fall. You drop something, it falls. Okay, that's the type of acceleration we just experience so intuitively all the time in our lives. Okay, because we live on Earth, we live on a planet, we don't live in outer space, we're not floating around. Okay, so free fall occurs when the only force acting on a falling object is gravity. Okay, so it means negligible air resistance, negligible friction. All right, that is a state of free fall. All right, and free fall has some very specific quantities. The easiest to remember is that the speed of free fall accelerates at 10 meters per second for every 1 second of free fall. So the moment you drop something, you drop it from rest. Well, 1 second later, it's traveling at 10 meters per second. After free falling for 2 seconds, it's now traveling at 20 meters per second. After free falling for 3 seconds, you guessed it, 30 meters per second. Then it goes up to 40 meters per second after 4 seconds. After 5, 50. Every second it speeds up by that much. That means that the distance it covers is not the same, right? Because since it was moving on average in that first second, when it went from 0 to 10, we say it was moving on average 5 meters per second to go from one to the other, it covered this distance. But then in the second second, where it had a much greater average velocity, because it started that second at 10 meters per second and finished it at 20 meters per second in terms of its downward speed, well, of course, it covered a greater distance, right? And that relationship of how much more distance it covers is actually parabolic. It's growing with the square of how far it's traveled, all right? So if a falling object gains 10 meters per second, each second it falls, its acceleration is 10 meters per second, 10 meters per second, both of them, or neither. Which one's an acceleration? Well, I haven't talked about the units of acceleration yet, but since it's velocity per time, so v over t, and the units of velocity are meters per second, among other units, but that's the most important for this class, and the units of time are seconds, then we get that acceleration is meters per second squared. That's how we say it. We say acceleration is meters per second squared. All right? It is common to express 10 meters per second as 10 meters per second squared. It's the most common. Okay? So a free-falling object has a speed of 30 meters per second at 1 instant. Right? So this is an instantaneous downward speed. Exactly 1 second later, its speed will be, what's the rule I was talking about? All right, you should know this one, 40 meters per second. Okay? So the distance fallen by a free-falling body, okay, it's free fall, only gravity. Does it remain constant each second of fall? Does it increase each second when falling? Or does it decrease? Which was it? It increases. The falling distance is proportional to the time squared. That's what I meant when I said it's parabolic. Okay? Here are the values. All right, so you start something from rest. So that means that the moment it starts, it hasn't gone anywhere, so it isn't moving yet, and it hasn't fallen, right? We just start the clock, right? At the starting line. Then we drop the object and we watch it fall. After 1 second, it's falling at 10 meters per second, and it's covered a distance of 5 meters. Okay? After 2 seconds, it's now traveling at 20 meters per second, and it's covered 20 meters. All right? And we know these ones, 30, 40, 50, but look what happens to the distance traveled. As I said before, it doesn't go up steadily like the velocity. Instead, it grows parabolically. It grows with the square, all right? In fact, it grows with 1/2 times the time squared times gravitational acceleration. So the distance, all right, distance fallen, d for distance fallen, is going to be equal to 1/2 times 10 meters per second squared times the time it's fallen squared. That's where those numbers come from. It's exact, plug them in, that's exactly where they come from. All right, thank you so much for watching this introductory lecture on the physical sciences, starting with the basics of physics. See you next time.